Okay, hi everyone, good afternoon. Thank you so much for the organiser for inviting me. It's great to be able to come here today before all the Amplitudes events are happening at the end of June, start of July. So yeah, I'm a first year DPhil student at the University of Oxford, but I was also at the Perimeter Institute last year. So I suppose this talk is kind of a mesh of kind of interests that are that I pursued at PI and also some of my interests as a DPhil student at Oxford. So I'm going to be taking a slightly different motivational approach to what Theo was talking about earlier today. So essentially I'm talking about scattering amplitudes without diagrams. So what we're going to do is we're going to look at a reformulation of amplitudes at tree level that basically goes straight from the particle content. We're going to bypass the Lagrangian and traditional Feynman diagrams all the way to the actual amplitudes itself. And this is the CHY formulation of scattering amplitudes. And then also in part two, after I talk about that, I'll talk about its parent theory of Ambitwistor strings because we like to know where things come from. So as motivation, what we taught, so like amplitudes in about 1955, the LSZ reduction theorem related time or basically allowed us to evaluate S-matrix elements as from time-ordered correlation functions. And then when we go to the momentous space, we get our Green's functions, which reduce to amplitudes at simple poles when we take the on-shell limit. And traditionally how we compute them is through perturbative Feynman diagrammatic procedures. So we have our standard rules that we're all familiar with, but traditional methods, even at tree level, can be combinatorially quite expensive. There's an explosion of diagrams even at tree level, and also loop integrals can become quite complicated, although there's some great work done in studying structures of amplitudes, just as like Luke and friends were talking about today, and stuff. But for us it can be a computational hardship. But to motivate like a geometric origin of amplitudes, the final answers even tree level look quite simple and nicely and compact. So in 1986, Park Taylor published a 4-page paper where they very nicely and neatly wrote down the MHV tree level amplitude for all different multiplicities. And as you see in the spinor helicity formalism, it's quite compact. So this begs the question, makes us answer the question, do amplitudes have a geometric origin? And so the story continues. So we got Nair in 1988, who related MHV amplitudes to current correlators on a 2-dimensional Western-Witten model on a CP1. So kind of CP1 being mentioned, kind of the red light went off to ask, is twistor theory in the picture? And 2003, Witten came out with this groundbreaking paper on the twistor string, and it geometrically encodes n = 4 super Young-Mills amplitudes. And then the dream came true in 2004, where Rowan, Sprolich, and Volovich actually calculated tree amplitudes as integrals over moduli spaces of holomorphic maps between n-punctured Riemann spheres and these nice holomorphic curves on twistor space. So using all this geometry, this nice geometrical structures there, can we break from the perturbative story and actually get tree amplitudes in theories that we know and love, like Young-Mills or gravity? And it turns out we can. So part one of the talk, I'm going to talk about the CHY formulation of scattering amplitudes. So amplitudes are going to be computed directly from the kinematic data. No diagrams are needed. So we're going to look at our kinematic invariants, so our poles of our amplitudes. We're going to connect them to punctures of a sphere. And we can think about these punctures as the locations of our external particles in our scattering experiment. And they're related by this so-called scattering map. And this map comes about at tree level for n massless particles to these so-called scattering equations, where there's a set of polynomial equations, n-3 of them are linearly independent, and they have n-3 factorial solutions where n is the number of external particles. All right, and as I hinted at in the previous slide, you can clearly see the relationship between the kinematic invariants and the punctures on the Riemann sphere. Now, I'm going to claim that they form the backbone of the tree-level S-matrix for massless particles in any dimension. And we're going to see this through the universal CHY representation of tree-level massless amplitudes. All right, and you can see here the stars of our show, the scattering equations, and they're kind of in these delta functions, sorry to all mathematicians here. Basically, we're looking at an integral over the moduli space of punctured Riemann spheres. So if you solve these set of scattering equations, you've got your amplitude, all right? So this structure is universal for a wide class of massless theories, going from Young-Mills gravity bijoint scalar theory all the way to DBI, nonlinear sigma model, Einstein-Maxwell scalar, and so on. Another important feature about this representation of our amplitude, in order to make sure everything's nice and gauge fixed, we need to divide by the volume of SL2C, because there's an SL2C redundancy on the punctures on CP1, because the punctures themselves are, this symmetry of Mobius transformations there. So I've said that these are universal for amplitude structures, but the theory creeps in through these building blocks. So essentially what we're going to be doing is doing Lego. So we have these theory-dependent half integrands, and these are going to be our blocks. So certain mathematical functions are going to encode the, say, polarization or the color data for different amplitudes theories. And I'm going to go through two different examples of these half integrands today. Now I do have an asterisk. This is indeed the full amplitude, tree-level amplitude for any dimension. It's dimension agnostic, which is nice, for my massless particles. But this is just for theories without color or flavor symmetry in the external legs. So for like gravity, this is fine. But for, say, like Young-Mills or the bijoint scalar theory, where we have color or flavor symmetry, this is just the color stripped amplitude, or the partial or double partial amplitude. That was just a bit of a footnote. But let's go on to our theory-dependent half integrands. So let's encode color. So theories like Young-Mills have color symmetry, so gluons self-interact. And in our Feynman rules, this corresponds to our structure constants of the Lie algebra under which the symmetry occurs. And this is related to the punctures via a cyclical ordering of punctures on our sphere. And this is encoded through the Park-Taylor function, right? Where we have our punctures on the Riemann sphere, and they're undergoing a specific ordering in rho. So every time we see color or flavor in a theory, we're going to put in this building block into our CHY amplitude. All right, so that's color done. What about polarization? So polarization is encoded by the, and also kinematics, it's encoded by the reduced Pfaffian of an antisymmetric matrix. So let's break it down. So we're going to start off with this very nice matrix of 2n entries, n being the number of external particles, and it has this beautiful block structure. It's antisymmetric, and you can see the polarization encoded in our B and C blocks right here. So this is the matrix. This is what's encoding our polarization and kinematics. And just to give you a brief sense of what the Pfaffian definition actually is, if you take the Pfaffian of our antisymmetric matrix squared, that's just going to equal to the determinant of that matrix. So it's like the square root of a determinant. Again, sorry for the vague definition, mathematicians in the room. So the reduced Pfaffian is the thing that we want, because due to momentum conservation and other symmetries of this matrix, it turns out that when we evaluate the Pfaffian, it's just equal to 0. So if we eliminate 2 rows and 2 columns, it's permutation invariant, so we can pick whatever 2 rows or 2 columns we want. We get the correct integrand that we want, and this is, we did a sanity check on dimensional analysis, and this is nice. So we now have color, we now have polarization. Let's look at a little table. So I'm going to introduce the 0th copy and the doubled copy, which we've heard a lot about the double copy today. So let's look at a spin 0, a spin 1, and a spin 2 theory. So spin 0 theory, a scalar theory that we get out of CHY, is actually the bijoint scalar theory. So it came out of this formalism. It's the quantum field theory behind the icosahedron. And has only planar diagrams, so you can do nice combinatorics with Catalan numbers. But when you put in 2 Park-Taylor functions in here, you're going to get a scalar field theory. Now, if you replace a Park-Taylor with a Pfaffian, you're going to get Young-Mills theory. And this makes sense because in Young-Mills, we've got one kind of color label associated with each external leg, and we also have polarization encoded there too. So this is kind of why it's known as the 0th copy right here. And then the double copy is that we replace this, we move away from this Park-Taylor and we add in another reduced Pfaffian of this matrix and we get gravity. So you can see this double copy in this nice kind of structure here. And just using a very nice property of the scattering equation solutions called KLT orthogonality, which if you look at any Sebastian Mazera papers, that's the best place to look at that. KLT orthogonality of the scattering equation solutions has kind of origins in string theory, but it means that you can kind of glue that these half integrands together to get various theories from one another. And these aren't the only theories that you can get. As I mentioned beforehand, you can use various different integrands and different matrices encoding polarization and kinematics to get different theories. As well as using KLT, you can use various things like compactification and or other CHY kind of techniques like scaffolding, and you can build one theory from the other. So there's a really nice structure, there's a really nice relationship between all these different. And what I've been working on, I'm just going to pop this slide up mainly to show off. Oh, sorry.
Can you get fermions?
Sorry?
Can you get fermions?
Yes, fermions should be coming in. I think I'll talk more about, how fermions are encoded in matter fields when I talk about Ambitwistor strings. So there are fermions in like the above theory, but yeah, there should be there. But yeah, so I should stop. Does anybody have any questions? Is everything clear so far? Hopefully I'm not talking too fast or anything. Yeah, Alex.
I have a question about if you like the table, please. So when we say the double copy is you take the square and then
a tree level, yeah.
does that hold for the IL and IR? Like if you just take the square that.
Yeah, so yeah, okay, so these KLT orthogonality relations, it's just you have this kind of matrix that you have that's entirely in terms of the kinematic invariance and stuff, but it also depends on your kind of color orderings here. So what happens is when you kind of absorb the integrands together through this KLT orthogonality, it kind of absorbs that color, and that's where you get the Pfaffian squared property. I suppose just briefly, I've been working on this topic in my master's, and it's turned into various projects now in my depot with different groups. So I've been looking at different nice structures in the biojoint scalar theory and also other theories. So mainly just wanted to show off with Higgs diagrams. So I've worked on massive scalars. So a nice feature of CHY is you can build this what we call the scattering potential. When you extremize it, you get your scattering equations. So we built a nice formula, and it actually derived the massive equations that were came out about 12 years ago. And then we looked at some combinatorics, we looked at off-shell scattering, and what happens when some of our kinematic invariants are 0 in these polynomial equations, and how we can build correlation functions from, or amplitudes that give rise to correlation functions. And you can do this by this very nice double color structure.
In this context of off-shell scattering, X energy of
so what I mean with off-shell is that we made a specific choice for our off-shell. So we had an on-shell momentum, and then we kind of had this reference we had this reference vector that kind of parameterized an off-shellness. And our kind of goal was to see whether or not we could get amplitudes from correlation functions, and some of these guys ended up being 0. But as far as I'm aware, momentum conservation still holds in what we were looking at. But this is a very kind of new topic that me and a group in Leipzig are hopefully going to merge 2 of our papers together and find out more. So yeah, but we can chat about it more. Okay, I'm going to zoom through Ambitwistor strings. So CHY. it's nothing like a space-time action or conventional string theory, and the underlying physics actually turns out to be Ambitwistor strings. Okay, so we're going to try and build an Ambitwistor string in whatever time I have remaining. So Ambitwistor space. So we're not gonna limit ourselves to the 4 dimensions of twistor theory. What we're going to do is we're going to start with complexified Minkowski space in d dimensions. We're going to take our cotangent bundle. Okay. So anyway, we want to encode momentum, and we want to find the space of null directions because again we were associated with massless scattering. So we have a subset of our cotangent bundle, and then what we're going to do is to get to projective Ambitwistor space, we would like to mod out by our various redundancies so that all of our degrees of freedom are nice physical. So like scalings and shifts in space time along each null direction. Then we have this projective Ambitwistor or Ambitwistor space. All right. Now word-line quantum field theory. I'll zoom through here. So you have your Feynman propagator. You do your Schwinger parametrization. You get your second-order path integral all over the world line, and then your Feynman diagrams are just going to be your world lines glued together. But again, we want momentum into the picture, and we would like a nice first order action. So the second order action I had previously, this is just the first order action version of it. And to enforce null constraints, we introduce this Lagrange multiplier. And again, the gauge transformations of this first order action correctly give us the same gauge transformations, or similar to the ones we had previously when we were trying to mod out these null translations generated by P and also. So solutions to these field equations, modulo gauge, are null geodesics in spacetime, parameterized by the scaling of P. So how do we build an Ambitwistor string? We're going to go from a world line to a world sheet, because Ambitwistor strings are quantum field theories of holomorphic maps from a Riemann surface to projective Ambitwistor space. So our projective Ambitwistor space is going to be our target. It's where our x's and our p's are going to lie. Now we're going to complexify space-time, look at our cotangent bundle, make sure everything's nice and holomorphic, build kind of this holomorphic derivative, this d bar. So everything splits into holomorphic and anti-holomorphic coordinates. We have our one form which looks like diffeomorphisms on our world sheet, and we're going to build the bosonic action of our Ambitwistor string, right? And again, it has the same kind of similar nice gauge transformations we saw previously, and our null constraint or massless dynamics constraint is satisfied by this Lagrange multiplier, and so our target space is Ambitwistor space. And so how do we kind of mimic what was going on in CHY? So again, to highlight the double copy, you split these kind of action or matter fields into your left and right components. And again, just like in CHY with your half integrants, whatever you choose will dictate, what's going on in whatever theory you're looking at. So for instance, to mirror what we saw earlier, current algebras, you can construct to add color into your world sheet. So these currents are going to have some Lie algebra index. They're going to satisfy this OP, and we can build our matter actions from those, which could include fermions and not. Now, this world sheet super algebra here introduces our fermionic degrees of freedom, a fermionic gauge field, and what this guy is going to do is it's going to be the parent action of our Pfaffian, all right? And again, it has some, we have our fermionic supercharge here. It's nice, first order action. Okay, so this is going to encode our polarization or our Pfaffian from before. This is going to encode our color, and we can build a table kind of like before with the Ambitwistor string and our CHY. So again, every time we see color, we put in a current algebra. For every time we see polarization, we're going to put in a world sheet super algebra. And how we get the CHY amplitudes is that it's very much like a string theory amplitude computation. You take your path integral, you insert your vertex operators that impose constraints, and you make sure all of your gauge redundancies are taken care of. And these vertex operators represent our external particles. When you compute their correlator, the path integral localizes on the scattering equations. And basically that's just a quick summary of how you can get your CHY amplitude from this parent theory. But I think overall, broadly speaking, these ambitwistor strings contain a lot more information than the CHY formulation do in terms of amplitudes and whatnot. So as a final bit, twistors give a geometric description of amplitudes, but ambitwist in 4D, but ambitwistor strings extended to all dimensions, and they're the parent theory of CHY amplitudes, and the scattering equations arise from universal world sheet theory. And they're also what you can do. My supervisor, David Skinner, and lots of different people have been working on how to bring this to loop level. So the scattering equations in double copy beyond tree level. There's some nice papers there. You can work on massive extensions and also bring this from a flat space to curved backgrounds. Right, thanks for listening. If you have any questions, we can discuss later now. All right.
Thank you very much for the very nice talk. Have any questions? Yes.
I mean, the ambitwistor strings follows. It's just like the scattering equations are going to be quite different. Like for instance, I believe the scattering equations at loop level do contain the loop momentum as well, and stuff like that. So yeah, there is a description. I think David Skinner and Tim Adamo have nice papers.
Also accommodates or also gives you
as far as I'm aware, but yeah, because again, these ambitwistor strings they kind of gave. Again, they contain a lot more information than what the tree level CHY formulation do. So it was kind of easier to construct according to information about what's going on at loop.
How easy slash?
Yeah.
Yeah, this one.
It's doable in the sense that polynomial equations not that easy to solve, all right. But there's a couple of things you can mention. So it turns out that these kinematic invariants, right, that you can go into this positive region. You could pick a basis for your kinematic invariants, because you can't use all of them because you have momentum conservation constraints going on there as well. And then basically when you pick this positive region, all your solutions to the scattering equations will be real. And then you're tasked with actually solving these polynomial equations. And again, we're not completely done with the combinatorial problem because there are n-3 factorial solutions. So it's fine when you're at 4 points, you only have one solution. Gauge fix 3 particles. But yeah, it can get quite complicated at high order. So there are ways to combat that using mathematics and various other techniques. Like I've been working on something that we have a reduced number of scattering equation solutions when you go off shell. But yeah, but once you kind of solve them, you get your determinant. Your Jacobian, which turns out to be your determinant. Then it's just your pre-dependent half integrands multiplied by or divided by this. But yeah, that's why we get algebraic geometry. Yeah, help us with that. So yeah.
Okay, let's thank our speaker again.